Alright, we'll start now. Good afternoon, everyone. So, once again, I welcome you all for the problem solving session for the NPTEL course Fluid and Particle Mechanics. And the course code is NOC 25CH49. And the course instructors are Professor Sumesh P. Thampi and Professor Basavaraj M. Gurappa from the Department of Chemical Engineering, IIT Madras. And the live sessions are handled by myself, Ainkara Kartiga. I am a research scholar from the Department of Chemical Engineering, IIT Hyderabad. So this is a 12 weeks course, Fluid and Particle Mechanics, and we are almost towards the end of the course, week 11. So far we have seen about introduction to Navier-Stokes equation, exact solution, Taylor-Quid flow rheology, dimensional analysis, turbulent flow, friction losses, Moody's chart, boundary layer theory, like exact boundary layer and all comes next in week 12. And apart from that, introduction to particles, their characterization, particulate phenomena, Brownian motion, motion of particles in a fluid, terminal velocity, particle separation, and sedimentation of dilute, concentrated, and flocculated dispersions, and packed and fluidized beds, and filtration. So far we have almost covered everything, and like a few concepts are left, that is boundary layer theory. And yeah, in today's thing, it would be mostly pipes connected in parallel or in junction. So those type of problems we'll see in today's class. So for books and references, we have mostly you would have almost covered unit operations of chemical engineering by Baron Lee McCabe, and fluid mechanics by Frank M. White, and introduction to particle technology, Martin J. Rhodes. And references are Coulson and Richardson's Chemical Engineering, and Fluid Mechanics by Piyush K. Kundu, and Principles of Colloid and Surface Chemistry by Paul C. Hymans and Rajagopalan. And finally, we have Transport Phenomena by Bird, Stewart, and Lightfoot. So, in week 11, what the concept wise that was covered by the professors were momentum and kinetic energy factor, pressure drop in pipes when connected in series, pressure drop in pipes which are connected in parallel, and pressure drop in pipes which are connected at a junction, and boundary layer, like introduction to the boundary layer. So we'll start with the problems. So first problem is this one. So we'll first see what is given about the problem in the statement. So what is given is we are asked to consider an elbow duct as shown in figure 1. So we have an elbow duct which is making a 30-degree at the outlet, and in the inlet it is nearly horizontal, and inlet diameter is 25 centimeter and outlet diameter is 30 centimeter. A liquid of density 840 kg per meter cube and viscosity 190 millipascal second is flowing through the duct at a rate of 0.1 meter cube per second. So we are given the fluid properties which is flowing inside the duct, and also we are given the flow rate at which the fluid is flowing. So fluid has having a density of 840 kg per meter cube and viscosity of 190 millipascal second, or it is 0.19 pascal second. And we are given the diameter. So from what general inferences which we can is, so flow rate is given, so what we can get the velocity at the inlet and the outlet. Because we know the diameter of the pipe at the inlet and the outlet, what we can do is we can get the area, cross-sectional area of the inlet and the outlet, and by using the cross-sectional area we can get the velocity. So that is one thing which is straightforward. And from velocity, what else we can determine? We can determine the Reynolds number. So Reynolds number is rho v d by mu. So we know everything in that. Rho and mu are fluid properties given directly in the question, and we can calculate from the cross-sectional area and flow rate, and d is directly given. So Reynolds number we can get it directly, and if we know the Reynolds number, we can get the friction factor, and subsequent calculations we can use that directly. So what are all the problems that are coming after this is a few straightforward problems wherein you will be asked to calculate velocity and so on. So we'll start now. So first is the average velocity at the inlet section 1. So we know that this is inlet and this is outlet. So section 1 is inlet, section 2 is outlet. So average velocity at the inlet section 1 is dash meter per second. So as I mentioned, we need to calculate the flow rate. Okay. We need to calculate the flow rate divided by the cross sectional area. That will give us the velocity at the inlet, that is section 1. So we will see how we can do that. So first let us see what is given in the question. In the question, what was given? We were given a flow rate and the diameter of the pipes. So while using that, flow rate is given as 0.1 meter cube per second, and diameter 1, that is the diameter of the pipe at the inlet section, is given as 25 centimeter, or it is 0.25 meter. And okay, we are just calculating for the inlet, so let it be. So what we need to do, we need to find the velocity. So velocity is actually q by a. So here, since a is, just a minute. Yeah. So since A is corresponding to the inlet section, we need to use the diameter 1. So V is equal to Q by A. So it is meter cube per second divided by meter square. That gives us meter per second. So unit wise also we can use it to remember it easily. So flow rate divided by the cross sectional area gives us the average flow velocity. So in this, what is unknown? Q is given, A1 is unknown. So A1 is cross sectional area. So it is pi r square r pi by 4 d square. So it is a cylindrical or pipe, and its cross sectional area is a circular cross sectional area. So on that basis, we have calculated the area. So we'll now substitute it directly in the problem. So it is pi by 4 d1 square. So d1 here is 0.25 meters. So we can directly substitute it in that. So it is 3.14 divided by 4 into 0.25 square, that gives us 0.0491 meter square. So this is the cross sectional area. So now after we got the cross sectional area, what we need to do? We need to put it back in the original velocity formula, and there what will we get? V1 is equal to Q by A1. So Q is the same at the inlet of the and the outlet. So it is V1 is equal to 0.1 divided by 0.0491. So that gives us 2.03 or 2.04 meter per second. So whatever value we can use, we can get. So that is the V1. So this is how we calculate the velocity at the inlet. So then, yeah, 2.0367 meter per second. So we'll now go to next question. The average velocity at the outlet is dash meter per second. Q is equal to point. Okay, so now we have to calculate the average velocity at the outlet section. So section 2. In section 2, what was the diameter? It was diameter is 10 centimeters. So it is 0.1 meter. So in the same problem, we just need to change the numbers. So we'll see that. So it is given that 0.1 meter cube per second, it remains the same, and d2 is 10 centimeters, so it is 0.1 meter, and formula remains the same. V2 is equal to Q by A2, and A2 we need to calculate again. A2 is equal to pi by 4 d2 square. So pi is 3.14 divided by 4 into 0.1 square. So that gives us 7.85 into 10 power minus 3 meter square. So we are just substituting it. A2 is equal to 3.14 divided by 4 into 0.1 square equal to 7.85 into 10 power minus 3 or 0.00785 meter square. Now what we need to do, we found out the area, we need to substitute it back in the velocity formula. So velocity is equal to flow rate divided by the cross sectional area. So now we have to put this area in there. So it is V2 is equal to Q by A2. Q is 0.1 divided by 0.00785. Oh, it is not, it is 137. It is 12.7389. I'll check again. 0.1 divided by 0.00785. So yeah, it is not changing. It is 12.7389 meter per second. Just a little typo over there. But yeah, now that is V2. So now we have found out V1 and V2, that is velocity at the inlet and velocity at the outlet also we have calculated. So how did we calculate? We are given the flow rate and we know the diameter of the inlet and the outlet. So we have just divided the flow rate divided by the cross sectional area of the pipe, and cross sectional area here it is a circular cross section, so it is pi by 4 d square. So after that we used, and it is a simple approach. Now let us go to question 3. In question 3, what is given is that Reynolds number at the inlet section is dash. So this is what I mentioned in the beginning. So once we calculate a few things, we can calculate the entire property of the flow system. So first we know the in the question it was given just the diameter and the flow rate, but from sequentially we can get whatever properties we desire, we can get it from there. So here the first one is Reynolds number is equal to rho v d by mu. So rho here is actually density of the fluid, and v is the velocity of the fluid at the inlet, and d is the diameter of the pipe at the inlet divided by mu, again the viscosity of the fluid. So rho and mu values are given in the question. So it was something we will see when we do. So we calculated in the previous question, and now d is also given straightforward in the question. So now we need not do anything, we can just substitute it and we can get the solution. So what is happening is, what is given, rho is 840 kg per meter cube. I'll just check once what was the density like that. Yeah, 840 kg per meter cube and 0.19 pascal second. So it is 840 kg per meter cube, and mu is 190 millipascal second, or it is 0.19 pascal second, and d1 it is 25 centimeter. It is in SI units it is 0.25 meters. So we know rho v d by mu, and we calculated in the previous, we can mention that it is not given, but it is calculated from Q1. There is one more problem also. So now we know everything required to calculate the Reynolds number. So Reynolds number is equal to rho v d by mu. So when we are substituting, it is Reynolds number is equal to rho is 840, and 840 into v is 2.0367 into d is 0.25. divided by 0.19. So that gives us Reynolds number as 2251.09. So what we can say is it is less than 2300. So the flow is kind of a laminar. So that's why we calculate the Reynolds number, right? To determine which regime of flow is happening. Laminar or turbulent or in the transition zone. So here it is less than 2300 in a pipe flow. So we can say it is a laminar condition. And what is Reynolds number? Reynolds number is the ratio of inertial force to the viscous force. So here kind of viscous force is kind of uh, dominating compared to the inertial force because velocity here is low. So that is the thing. Compared to next at the outlet, I mean to say. So what we can is we can see the next one. Question 4. Reynolds number at the outlet section is dash. So it is 840 kg per meter cube. Again, it is like a direct thing where we have to substitute the value. So it is density is 840 kg per meter cube and viscosity is 190 millipascal second and it is 0.19 pascal second. D2 is 10 centimeter and V2 is 12.7389 meter per second. Formula it is rho v d by mu and solution it is 840 into 12.73 into 89 into 0.1 into 0.19. So it is 2 not, oh sorry, divided by 0.19, right? 5631.934. Again it is comparatively high, so it is kind of near the turbulent regime. So that is what we can say from this question 4. So now we can move to next question. Assume that the flow is laminar at the entrance and turbulent at the exit. The momentum correction factor at inlet and outlet respectively are dash. So what is given? We are asked to assume the flow is laminar at the entrance and turbulent at the exit. So which we also like kind of got values closer to that. The momentum correction factor at the inlet and outlet respectively are dash. So here it is flow is laminar. So why do we use momentum correction factor? To account for the non-uniform distribution of velocity in the flow in the real time applications. Theoretically, we assume it to be uniform velocity fields, but in reality, it may not be uniform sometimes. So to account for that, we use the momentum correction factor. So here in the question it is asked like we are asked to assume the flow is laminar at the inlet and turbulent at the outlet. So what will be the momentum correction factor at the inlet and outlet respectively. So here we can do the derivation and we can get the value similar to how we got it, like there is a formula, right? U by u, that square dA integral of that. So we can use that and we can get the values, or otherwise mostly it will be like in the range of around 1.3 for laminar and 1.03 for turbulence. So here I haven't shown the like derivation or a step-by-step process. If you want, you can try that as well. You will end up with the similar results. So now moving on to question 6, what is asked is, neglecting any pressure and viscous effects, compute the force acting on the duct due to momentum change only. Use the integral relationships. Just a minute, I'll just close the windows. It is Okay, so what we are doing is we are asked to neglect any pressure and viscous effects and compute the force acting on the duct due to momentum exchange only. So we'll start now. So and we are asked to compute the x component and y component of the force separately. So we are given that density is 840 kg per meter cube. Viscosity, flow rate is 0.1 meter cube per seconds. Meter cubes per second. D1 diameter at the inlet is 0.25 meters and D2 is 0.1 meter or 25 centimeter and 10 centimeter. And theta, that is the angle at which pipe 2, that is outlet, is kind of inclined, is 30 degrees. So now we will start. So what we can say is we have to calculate the area and at the inlet and area at the outlet. So this we have done in previous problems as well. So it is pi r square or pi into d by 2 the whole square or pi by 4 d square, whichever it is. So it is 3.14 into 0.25 square divided by 4. So it is 0.0491 meter cube, sorry, meter square. And next thing what we have to calculate, we have to calculate the area, cross-sectional area at the outlet. So what is the cross-sectional area at the outlet? So value wise it is 3.14 divided by 4 into 0.1 square, which we calculated in the previous steps as well. So just to rewrite it. So it is 0.00785 meter square. So we have calculated the area 1 and we have calculated the area 2, that is the inlet cross-sectional area and the outlet cross-sectional area. Now average velocity at the inlet is q by a1, again it is be calculated as 2.0367 meter per second, and average velocity at the outlet. So 1 here signifies inlet and 2 here signifies outlet section. So as mentioned in the problem only, I am not using any notation different. It was given in the question, so I am just using exact thing given in the question. So we are calculating the V average, that is velocity at the inlet and velocity at the outlet. These things we have done previously only. So there is nothing extra we are doing till here. So I'll just check one more time. 0.1 divided by 0.0491. It is 2.0367 and 0.1 divided by 12.7389, and that is okay, sorry, 0.1 divided by 0.00785, that is 12.7389. So that is similar to what is asked in the question. So we are not doing anything extra here. Now we have to use the momentum correction factor, which we got from the previous problem. As I mentioned, you can get it after integrating as well, but here I am just using the default value. So beta is 1.3 at the inlet and beta 2 is 1.03, that is at the outlet, laminar inlet and turbulent outlet. So these are all the things which we calculated in previous steps, and these are all given in the initial question itself. So however, we have this much of data to use it for this particular question. So we can use it and proceed with the problem in our question in our hand. So what we have to calculate it, we have to calculate the force acting on the system. Neglecting any pressure and viscous effects, compute the force acting on the duct due to momentum exchange only. So due to momentum exchange only, we need to calculate the force. So Fx and Fy we need to calculate. So yeah, now when we talk about solution, inlet section is purely axial flow because like it is a horizontal pipe at the inlet. So D1 is 10 centimeter. So if we take the components, what happens is that V1x is average 1. So it is 2.0367 meter per second. If you want to integrate it, it is into cos 0, so it is 1. So you are getting the entire value. V1y component of the velocity acting at the inlet is kind of a 0 because flow is happening in this direction. So only x component has the velocity. When we talk about the outlet section, however, we have x component velocity, also we have y component velocity because the pipe is inclined at a certain angle, that is 30 degree in our case. So outlet is at 30 degree. So we have to resolve the vector into x and y components. So V2x is equal to, we average, that is in this outlet section, so we average 2 into cos theta. So we average 2 into cos theta is cos 30. So it is root 3 by 2. So cos 30 is root 3 by 2. 12.7389 into root 3 divided by 2. Oh, okay. I think it is kind of a wrong value. 3 divided by 2, 11.03 meter per second. It is 11.03 meter per second, and sine theta is sine 30 is 1 by 2, right? So it is 12.7389 into 1 divided by 2, 6.3694 meter per second, so or 6.37 meter per second. So here we have to change, wherever I use 9 we have to change it, so that is the only difference we will be doing. I'll check one more time. However, cos 30 is 0.866 into 12.7389. Yeah, it is 11.03 meter per second. So it was a mistake from my end. So x component velocity at the outlet is 11.03 meter per second, and y component velocity at the outlet is 6.37 meters per second. So now what we got, we have to continue there. So it is 1.03. Okay, I'll just go step by step, wherever required I'll just go and make changes. So we have to calculate the momentum flux. So we are asked to use only the momentum variation and calculate the force acting on the duct, ignoring all other effects. So first we have to calculate the momentum flux. So it is m is equal to beta, that is the momentum correction factor, into rho into q into v. So what is this? It is like it should be like, ideally we use mv, right? Like m is mass flow rate, but we don't know the mass flow rate, so we are using the density into the volumetric flow rate. So on direct substitution, what we will be getting, 1.3 into 840 into 0.1 into 2.0367. So that gives us 222.41 for momentum flux in the inlet at the x direction, whereas in the y we have it 0, so it becomes 0. And similarly for the x component momentum flux in the outlet section, we have beta into rho into q into v2x. So here we need to do that change. So beta here is 1.03. Again, beta is varying at the inlet and the outlet, which you need to be aware of. Why it is varying? Because it is laminar at the inlet and turbulent at the outlet. Also, it is mentioned clearly in the question, assume inlet is laminar, outlet is turbulent. So we should use the momentum correction factor for the laminar at the inlet and for turbulent at the outlet. So now beta 1 and beta 2 we have given. So next is yeah, I'll change this alone. So yeah, we'll change it once we go back. So momentum flux in the y direction at the outlet is beta 2 into rho into q into v2y. So it is 6.37 into 0.1 into 840 into 1.03. That gives us 551.13. So this is calculated. We'll just change this value alone. What are we getting here? 11.03 into zero point 0.1 into 840 into 1.03. So that gives us actually 954.315 or 32. So what we need to do, net force acting on the duct in the control volume is given by a momentum flux at the inlet minus the outlet. So so it can be like outlet minus inlet also. So I'm just ignoring the sign because you can take outlet minus inlet. So it is m1x minus m2x is equal to 222.41 minus 954.32 actually 954.32. So that gives us 954.32 gives us 731.91. Oh, sorry. 731.91. So we are just subtracting in the x direction in the inlet and the outlet. So difference between inlet and the outlet. So this gives us, and similarly for y it is constant because in the inlet it is 0. So it is 551.13 minus 0. So that gives us 551.13 Newton directly. So yeah. So that is how we solved it. Net force acting on the duct. So we'll just see a quick recap actually. Okay, first we are writing the given and we are calculating the cross-sectional area at the inlet and the outlet, and based on that we are calculating the velocity at the inlet and the outlet, average velocity, and we are calculating the momentum correction factor at the inlet and the outlet as well, and we are also like having inlet as laminar and outlet as turbulent. And so after that we are calculating the x and y components of the velocity at the inlet and the outlet section separately, while in inlet it is straightforward because the flow is in horizontal direction, and outlet it is not so because the pipe is tilted at an angle of 30 degrees. So we need to account that while uh, like having the vector thing done while resolving the vectors. So after that we are resolving the velocity at the outlet into x and y components separately. Yeah. And then after that we are calculating the momentum flux in the x and y direction separately at the inlet and the outlet. And after that what we are doing, net force on the duct in the x direction is inlet minus outlet momentum fluxes. Similarly in the x direction, similarly for y direction we are subtracting the momentum fluxes in the x and y direction, sorry, in the y direction at outlet and the inlet. We are taking that difference and we will get the net force acting on the duct in the control volume. So that gives us fx and fy. So that's it for question 6. Now we will go to question 7 actually. In the previous calculations, you would have used the momentum correction factors. If you neglect the momentum correction factors, assuming beta as 1, calculate dash. So, okay, I'll just put. Okay, sorry. In the previous calculations, you would have used the momentum correction factors. If you neglect the momentum correction factors, assuming beta as 1, calculate. So now what we are asked to do, we are asked to calculate this problem, but by assuming the momentum correction factor as 1, we are asked to calculate it. So same problem, similar steps, we just have to use beta as 1 in place of 1.3 or 1.03, which we have used in the previous problem. So we'll start actually, yeah. So given is the similar thing. Once again, actually I have a, just give me 1 minute. Okay, so density is 840 kg per meter cube and flow rate is 0.1 meter cube per second. Everything is similar, just I am just rewriting everything. D1 is 25 centimeter or 0.25 meters. D2 is 10 centimeter or 0.1 meter, and theta is 30 degree, and A1 is the cross sectional area of the pipe at the inlet, so it is pi by 4 D1 square, which we calculated as 0.0491 meter square, and A2 is pi by 4 D2 square, which is 0.00785 meter square. After that, we calculate the velocity at the inlet and velocity at the outlet, which is flow rate divided by the cross sectional area, and we are getting 2.0367 meter per second and 12.7389 meter per second respectively for the inlet and the outlet sections. So till now we are clear with everything, and now beta 1 and beta 2 both are equal to 1, because in the question it is given that assume there is no momentum correction factor. That was the question. If you neglect the momentum correction factors, that is we are assuming beta as 1 by neglecting the momentum correction factors. So we have taken beta 1 and beta 2 as 1, and everything else remains the same. So first momentum flexes is okay. Okay. I'm just putting this slide, for no other reason than if you are using it later, you can verify it. So V1 is 2.0367 meter per second. So it is purely axial flow, and V2 we have resolved it into X and Y components. So it is 11.03 meter per second in the X and 6.37 meter per second in the Y direction. So after that, what we do is we have 11 point, here it is 11 point. 11.03. So momentum flux is m is equal to beta into rho into q into v. So we are calculating in the x and y direction separately at the inlet and the outlet sections. So first in the inlet section we are calculating the x component, which is like 1 into 840, so 840 into 0.1 into v1, that is 2.0367, that gives us 171.08. And next comes the Next comes the vertical component. At the inlet it will be 0. So now we are going to the outlet section. So it will be beta is 1 into 840 into zero point 0.1 into 11.03. So that is 926.52. And at the outlet it is 840 into zero point 0.1 into 6.37, which is 535.08. So net force acting on the control volume we are taking in the x and y directions, and it should vary now. So it is 926.52 minus 171.08, that gives us 755.44 in the uh, x direction, and similarly we can calculate in the y direction as well. That gives entirely from the uh, y I mean from the outlet section. Yeah, so 535.08. So what we did, the problem is similar to the problem which we solved in the question 6. What change we made? We changed beta 1 and beta 2 to 1. Both we kept as 1 here. We are just neglecting the momentum correction factor in the problem solution. So that's it. We are not making any other changes. So just we are neglecting the momentum correction factors and solving the problem similar to how we did. So there is nothing new in this. So yeah, we'll go to question 8. Okay, question 8 is, yeah, it is again a simple problem which I haven't solved it step by step. I hope like you can do it by integration, those things and all. But kinetic energy correction factors at the inlet and outlet are respectively. So inlet is like a laminar and outlet it is turbulent. So based on that, what we are getting is we are getting it as 2 and 1.075 respectively. If you do the integration and get the values also, you will get the same thing. Like you have to integrate it over that area, so you will get almost the same thing, only it just two like that is a very big steps now, that's why I don't include. But rather if you go to that formula and substitute the average velocity and substitute the uh, um, velocity and get the calculation done also. That is also uh, that also will give the same solution only. So that is for question 8. For question 9, what we have, the kinetic energy correction factor is used in fluid mechanics primarily because. Okay, here it is a theory question. So what is asked is, we are asked why we are using the kinetic energy correction factor in fluid mechanics and why. So kinetic energy correction factor is used in fluid mechanics primarily because dash. Option A, velocity is uniform across the flow section. Option B, pressure loss in pipes is negligible. Option B, pressure loss in pipes is negligible. Option C, velocity profile is non-uniform, causing the actual kinetic energy to differ from the calculation based on average velocity. And option D, density of the fluid changes with velocity. So as we all know, why we are using momentum kinetic energy correction factors, because the fluid velocity profile is actually non-uniform. Uh, So causing the actual kinetic energy to differ from the one calculated theoretically based on the average velocity. So that causes error. So that's why we are introducing the momentum and kinetic energy correction factors. So our answer is option C. The velocity profile is non-uniform, causing the actual kinetic energy to differ from the calculation based on average velocity. So that's why we are using this. So question 9 answer is option C. Now, okay, now we have a new set of a problem, and all questions will follow based on this particular thing only. So what we have is, first let us analyze the system actually. So we have two pipes connected in parallel, and we have a pump in the second pipe, and we have a fluid entering, and it is splitting into two pipes. So the pipe one length is 120 meter and diameter is 20 centimeter, and pipe 2 is having a pump, and it's the pipe 2 length is 15 meters and 10 centimeters, and the outer flow rate at the outlet section is 0.15 meter cube per second. So you all will be aware of, I'm just changing the numbers in the problems given in the assignment. So it sometimes it might not make actual sense with the numbers, but just see how it is done rather than following numbers and analyzing the logic behind those numbers. So that's my request. So coming back to the problem, we have a flow pipe where it splits into two pipes which are connected in parallel. So here the length of pipe 1 is, we call this as pipe 1, we call this as pipe 2, and the length is 120 meters and diameter is 20 centimeter at pipe 1. And for pipe 2, the length is 50 meters and diameter is 10 centimeter, and we have a pump here. And we have an overall outlet flow rate is 0.15 meter cube per second. So we'll see how. We'll read the problem statement now so that it will make actual sense. Consider the pipe system shown in the figure. Consider the pipe system shown in the figure. This is a galvanized iron pipe system and delivers gasoline at 20 degrees Celsius at a flow rate of 0.15 meter cube per second. If the pump is running and delivering 60 kilowatts to the flow in pipe 2, then determine the following. For gasoline, you may take the density to be 750 kg per meter cube and viscosity as 0.0002 kg per meter second. So we'll first understand what is given. So this is a pipe system and it is made of galvanized iron, and it is delivering gasoline at 20 degrees Celsius, and the flow rate is 0.15 meter cube per second, and the pump power is given as 60 kilowatts to the flow in pipe 2, and then determine the following. So for gasoline, we can take the density to be 750 kg per meter cube and viscosity as 0.0002 kg by meter second. So that is the thing. So pipe material property is given, and fluid property is also given. Like pipe material property is given in terms of like material in which it is made, and fluid property is given in terms of density and viscosity, and temperature is also given at which the flow is happening. So we can take the properties at that particular temperature, and flow rate is given and pump capacity is given. So we'll go to questions. So question 10 it is, the roughness height of galvanized iron in centimeter is dash. So we are asked to have the roughness height of galvanized iron, galvanized iron, and that too we are asked to give the answer in centimeter. So it is, oh, oh. Okay, point. So actually it is a straightforward value only. It is like reference height is 0.015 centimeter. It is taken from the theory based on the material properties. So we are not doing anything here. 0.5, yeah, it is in centimeter. It is 0.015 centimeters for the galvanized iron pipe. So that is question 10. This is the standard value used for friction calculations and resistance estimates in galvanized iron pipes. For galvanized iron pipe, the typical roughness height is 0.015 centimeters. This is the standard value used in engineering calculations for friction and head loss in pipes of this material. So that is the thing. So it is a standard value used in calculations when we are considering the galvanized iron pipes. So, before moving to question 11, we'll take a short 5 minutes break. Time is 3:55. We'll come back by 4. Because all the problems coming up are kind of continuation. So, I don't want to, like take a break in between. So, that's why we'll take a break and we'll come back and we'll finish it off. Because all the problems are kind of taken from the similar same problem actually, like continuation to the same problem statement given, so we can finish it off uh, at a stretch. Like I don't want to take break in between, so we'll come back after 5 minutes. Okay. We will start now. Hope you are back. Okay, so we have, or where we have stopped, we have stopped at the roughness height of galvanized iron calculation. I mean, it is not a calculation, rather it is a standard value. So standard value in centimeter was 0.015 centimeters. So now we'll proceed with the next question, that is question 11. The roughness ratio at the inlet and the outlet are dash. So we have seen how to calculate the roughness ratio in the previous problem. It is the ratio of the roughness height to the diameter of the pipe. So here we are asked to calculate the roughness ratio at the inlet and the outlet. So we know the roughness height of the galvanized iron pipe, and we know the value of the diameter of the pipe at the inlet and the outlet. So we can, straight away calculate the roughness ratio at the inlet and the outlet. So it is roughness ratio is equal to roughness height by pipe diameter. So roughness ratio at the inlet and outlet of the pipe system is so at the inlet where diameter is not 25 centimeter actually. Oh, it is 20 centimeter only. Roughness height at the inlet and outlet of the pipe. At the inlet it is a 0.015 centimeter divided by 20 centimeter. I am doing all the calculation in the centimeter. So it is 0.015 divided by 20, it is 7.5 into 10 power minus 4. Oh, sure. Something 7.015 divided by 20 is 7. Okay, this is 0075. Of course, it should be. I'm sorry, I missed that. But at the inlet it is 0.0075, and at the outlet it is 0.0015. So, okay, I think I have to do calculation wherever this particular thing is coming. So, yeah, you'll see that. For the following, you need, here it is just the ratio. It is the ratio of the roughness height to the pipe diameter, and we know the roughness height for the galvanized iron material of the pipe, and we know the pipe diameter, so we are just dividing it directly. So that is for question 11. And for question 12 we have, for the following you need to write down two equations. One containing the total volumetric flow rate is equal to volumetric flow rate in each pipe, and second relation being the relation between various heads and head losses. Once you solve the simultaneous relations, you can find the following. And velocity in pipe 1 and pipe 2 are dash. So we are asked to write two equations, one containing the volumetric flow rate and the other containing the head loss. So here the pipes are connected in parallel, so head loss will be equal in pipe 1 and pipe 2. So we can write as H1 is equal to H2, and but volumetric flow rate will be the sum of volumetric flow rate in pipe 1 and volumetric flow rate in pipe 2. So Q we know at the outlet it is 0.15, I guess, something meter cube per second. So that will be equal to Q1 plus Q2. Q1 is the volumetric flow rate of fluid in the pipe 1, and Q2 is the volumetric flow rate in pipe 2. So Q1 plus Q2 gives us the total flow rate, and H1 is equal to H2. That relation gives us that thing. So here we just need to use these two relations and get the values. So once we solve these two, we can get all other values. So that's it. Uh, so we'll start the solution actually. So question 12 solution, it is first we need to write the given. So length of pipe 1 is given as 120 meters and diameter of pipe, okay, length of pipe 2 is given as 50 meters and diameter of pipe 1 is 20 centimeter or zero point 0.2 meters and diameter of pipe 2 is 10 centimeter or zero point 0.1 meters. So now we have to calculate the area, cross-sectional area of pipe 1. So it is 3.14 divided by 4, that is pi by 4 d1 square, or 3.14 divided by 4 into d1, that is zero point 0.2 square. So that is 0.0314 meters square. Next, what we need to do, we need to calculate the cross-sectional area of the pipe 2. So pipe 2, it is 3.14 divided by 4 into zero point 0.1 square. So it is 7.85 into 10 power minus 3. So it is 0.00785 meters square. So same cross-sectional area of a cylindrical pipe. I mean, here the cross-sectional area is cross-sectional area of cylindrical pipe is a circular cross-sectional area. So the cross-sectional area is pi by 4 d square, pi r square or pi by 4 d square. So we are substituting the d1 value, the pipe 1 value and the pipe 2 value. So we will get the cross-sectional area of pipe 1 and we will get the cross-sectional area of pipe 2 as well. So pipe 1 has larger diameter, pipe 2 has smaller diameter. So based on that we are getting the area 1 and area 2. So now pump power is connected to pipe 2 is 60 kilowatts or 60,000 watts. And what else is given? Density of fluid is given, that is the gasoline is flowing at 20 degrees Celsius and its density is given as 750 kg per meter cube and viscosity is also given, that is 0.0002 kg by meter second. So these are all things that are given in the question and we are asked to find the velocity. So we'll find the velocity v1 and v2. And for solution, okay, first they asked us to write the two equations, one for the volumetric flow rate and the other for the head losses. So volumetric flow rate relation gives us equation in such a way that Q is equal to Q1 plus Q2 and here Q is nothing but 0.15 meter cube per second. So Q is equal to Q1 plus Q2, that is 0.15 meter cube per second, and H is equal to H1 equal to H2. Head loss is the same because it is connected in the parallel. So what is Q? Q is V into A. V is the velocity and A is the cross-sectional area and H is the head loss, which is HF is equal to FL V square by 2 dg. And F is the friction factor. Friction factor depends on the Reynolds number. Right. So what are we going to do? We are going to write it separately for pipe 1 and pipe 2. So H1 is equal to F1 L1 V1 square divided by 2 times of D1 into G. So Q, or we can put V is equal to Q by OA2. V is equal to, oh, okay, next slide. So V is equal to Q by A, and we are substituting that in the H1 formula. So it is F1 L1 V1 square divided by 2 D times of D1G. So V1 here is Q1 by A1. So F1 L1 Q1 by A1 square divided by 2 times of D1G. So H1 is equal to F1 into L1 is given as 120, and Q1 by A1 we calculated as 0.0314 square divided by 2 times of D1 into G. D1 is 0.2 meters, G is 9.81. So we are writing H1 as a function of F1 and Q1. So what happens? 120 into 1 divided by 0.0314 square divided by 2 divided by 0.2 divided by 9.81. So it is 31,016.5 into F1 into Q1 square. That is the relation we are getting for H1. Now similarly we have to do it for H2 as well. So H1, H is equal to FL square by 2dg, and here we know everything else apart from F and V. So V we can write as Q by A, and now we can write H as a function of F and Q. Rest everything is known from the question. So we are just doing that. So now we wrote it for question H1, that is for pipe 1 in the previous slide. Now we have to write the similar relation for pipe 2. H2 is equal to F2 into L2 into V2 square divided by 2 times of D2 into G. So here also V2 we can write it as Q2 by A2, and now it becomes F2 into L2 into Q2 by A2 the whole square divided by 2 times of D2 into G. And now we can substitute what are all the things that are known, and L2 is 50 meters and A2 is 0.00785 and D2 is 0.1, G is 9.81. So after substitution what happens? We 50 into 1 divided by 0.00785 square divided by 2 divided by 0.1 divided by 9.81. So that becomes H2 is equal to F2 into Q2 into 413,553. That is 4,13,553.49. So H2 also we got one relation, H1 also we got one relation, where H is a function of F and Q. That is the relation we obtained. So now what we can find is Q1 plus Q2 we have one relation, and we know H1 is equal to H2. What is unknown is F here. Okay, power is Q into rho into G into HF. Actually, I don't want to find it. Okay, power 2 is 60,000 kilowatts, and it is Q2 into rho into G into H2, and Q2 into rho is 750, G is 9.81, H2 is this one. Q2 into H2 equal to 60,000 divided by 750 divided by 9.81. That gives us 8.1549. Q2 into H2 is equal to this one. So, as I mentioned, one unknown remaining in the original H and F, H and Q relation is F. Where is my cursor? So now we need to determine F, so we can equate both the equation, and one more relation which we got is Q1 plus Q2, that relation we got. So by using those two relations, we will be able to get what is Q1, what is Q2, what is H1, what is H2, all those things we can know. So for first we will find F. So this is the formula which we used in the last class also. So Swami Jain explicit approach, and F is equal to 0.25 divided by log of epsilon by 3.70 plus 5.74 by Reynolds number to the power of 0.9 the whole square and the denominator. So epsilon by D is the roughness ratio and Re is the Reynolds number. So we'll see what to do now. So epsilon by D is known because it is roughness ratio we have calculated at the inlet and the outlet separately in the previous slides itself. So one thing is Reynolds number is still unknown. So Reynolds number is given as rho v d by mu. So Re is equal to rho v d by mu. So rho is fluid property, mu is also fluid property, it is known. So when we are calculating at the inlet, we can use Re is equal to rho V1 D1 by mu1. So D1 is known whereas V1 is unknown, but we can write V1 as Q1 by A1. So Reynolds number is equal to at the inlet, I mean not inlet, I am sorry, it is pipe 1. 1 doesn't mean inlet, it is pipe 1. I mentioned as inlet, sorry. So it is pipe 1, it is 750 kg per meter cube into V1 into 0.2 divided by mu, that is 0.0002. So what this gives us 750 into 0.2 divided by 0.0002. So that gives us 7,50,000 times of V1. So V1 we can again write it as Q1 by A1. So 7,50,000 into Q1 by A1. So A1 is 0.0314. So 7,50,000 divided by 0.0314. That gives us 23885350.32 Q1. So what is happening is it is actually what is that 23 million, sorry, million, 23,885,350, or in our words it is 85,000, 2 crores 38 lakhs 85,350 times of Q1. So it is a unusual, I mean it is a huge value. Similarly, what we can do, we can calculate it for the pipe 2 as well. So it is rho v d by mu. So v and d gets changed for the pipe 2. So v2 into 0.1 divided by 0.0002. So that becomes 750 into 0.1 divided by 0.0002. So it is 3,75,000. 75,000 times V2. So again V2 we are writing as Q2 by A2. Q2 is unknown, A2 is known. So A2 is 0.00785. So that again gives us a very huge value of 47,770,000 times 700.64. I think I left out 1 7 here. 4 it is 700 770 47 770 1 2 3 700.64 times Q2, it is not Q1. So now F is equal to this, both of these are actually huge values, right? So what we can do is we can actually neglect these values because 5.74 divided by Reynolds number to the power of 0.9. So Reynolds number is coming in the denominator. So we can kind of neglect these two, this particular term, and calculate the friction factor in pipe 1 and pipe 2 separately. I'll show you how it is not actually. Oh, I don't know why it became question 13 solution. We are doing 12 only, right? It is 12 only. I just change pipe 1 as 12 put 13 I'll put it again. Pipe 2 is dash. We'll come back there actually, because yeah, where we were, yeah, we'll just neglect this particular term because Reynolds number is very high value. So when it goes in the denominator, that number will be significantly small, so it won't affect us much. So I'll show you how it doesn't affect much in the later steps also after we calculate the values. So f1 and f2 we can calculate it now because it is 0.25 divided by log 10 to the power log 10 log base 10 epsilon by 3.7d denominator whole square. So now again it is 0.0075. So epsilon by d we know it is 0.0075. If you want I can write it here. Is the roughness ratio. So it is 0.0075 divided by 3.7 log answer square 0.25 divided by answer. So it actually changes, it is 0.01832, and the other thing remains the same, 0.0015 divided by 3.7 whole square, not whole square, log and then square 0.25 divided by answer 0.0217 or 0.022. Why this change? Because I kept it as 0.0075. While doing also I showed you, right, it was some mistake from my end, so it is 0.00075. If you want I'll check once again. 0.015 divided by 20, it is 7.5 into 10 power minus 4. It is not 3. So yeah, because of that I have to change in subsequent slides as well wherever it comes. So f1 is 0.018, f2 is 0.022, and again here also it is need to be changed. So leaving those, we'll do it right this time. So h1 is actually f1 times q1 square into 31,016.5. So f1 now it is 0.018. So we'll substitute that 0.018 into q1 square into 31,016.5 into. So that gives us actually 558.3, and H2 remains the same. F2 into Q2 square into 4,13,553.49, it is 0.022 into Q2 square into 4,13,553.49. So that becomes 0.022 into 413,553.49. 9098.18 q2 square. If there are any mathematical errors, please forgive me when if you are looking at it later stage. I tried my level best to like avoid error free, but the error we identified right now, right, similar things might be there, so just check for how to do, and don't take much thing from the numbers. So 9098.18 q2 square. So q2 into h2. Okay, this one we don't need. So now what is given? q1 plus q2 is equal to 0.15, and q1 is equal to 0.15 minus q2. This goes that side, and q2 is 553 point. Also, like I can remove the. Yeah, I'll remove the slide. H1 and H2 we have calculated, and Q1 plus Q2 is equal to 0.15. Q1 is equal to 0.15 minus Q2, and H1 is equal to H2. These two are the basic relations that we were using. And so H1 is equal to H2 means it is 558.3. Similarly, here also it is 558.3. 558.3. Q1 square is equal to 9098.18 Q2 square. So like this we got after substituting here. I think we can put it in the next slide. Because it is quite, yeah. H1 is equal to H2, so we are substituting what we got in H1 equation and what we got in H2 equation, and after that it is 558.3 into Q1 is 0.15 minus Q2 whole square equal to Q2 H2 is 9098.18 Q2 square. So that becomes, here it is 0.15 minus q2 square becomes a minus b the whole square equal to a square minus 2ab plus b square. So 0.15 square is 0.0225 minus 2 times of 0.15, it is 0.3 q2 plus q2 square. Here alone I need to change. So after that we are getting this equation. So it is this remains the same. We just So it is 558.3 into 0.0225, that is 12.56 minus 558.3 into 0.3, 167.49 Q2, 167.49 Q2 plus 558.3 Q2 square, 558.3 Q2 square equal to 9098.18 Q2 square. So 9098.18 minus 58.3, that alone changes to 8539.88 Q2 square plus, okay, this goes that side, this also goes that side, so it becomes plus 167.49 Q2 minus 12.56 equal to 0. So now we have to calculate it actually. Once again, 8539.88, 167.49 minus 12.56. Okay, so what happens is it is a quadratic equation now. So for ax square plus bx plus c equal to 0, so you can get the solution from that. X is equal to minus b plus or minus square root of b square minus 4ac divided by 2a. You can use that. It will be like mostly minus b plus square root of b square minus 4ac by 2a. So if we do that, what we will get is, okay, we'll do it in the next slide. So Q2 is actually minus 167.49 plus square root of 167.49 square minus 4, okay, times of A is 8539.88 into minus 12.56. Of 8539.88. Actually, like, I'll give you this. It is actually 0.02978. Okay, I'll just check once again. It is actually 859.88 into minus of 12.56 into 4 minus of plus 167.49 square root of this. Oh, okay, just a minute. 4 into 8539.88 into 12.56 plus 167.49 square. Oh, divided by okay, almost same only. So here it should be this one. Okay, so Q2 you can use this formula and get the solution, or you can straight away you get it from the scientific calculator, where you can go to mode, equations and degrees, and for degrees you can give 2, and you can give A, B and C values, and you can directly get the Q2 value. If that is where, if you are permitted for calculator, you can use that. So now we got Q2. So now we have to get Q1. Q1 is equal to Q2 0.15 minus Q2. So it is 0.15 minus 0.02978. So that gives us 0.15 minus 0.02978, 0.1202. 1202 meter cube per second. So we got Q1 and we got Q2, and H1 and H2 we need to calculate, which we will do it. Okay, it is not. We'll H1 and H2 will calculate in the next problem. Okay, we'll just calculate it normally just to confirm, Otherwise, if it is wrong, we can check it normally. So this is H1. So it is 0.1202 square into 558.3, that gives us 8.06 meters, and Q2 is 0.02978 square into 9098.18, that also gives us 8.0. Also we can use it later, so, or we can keep it here only, no issues. So v1 is equal to, in the question, finally, like we calculated Q1, we calculated Q2, and what is asked in the question is we are asked to calculate V1 and V1. So V1, that is velocity of the fluid in the pipe 1, is actually Q1 by A1. Again Q1 is different. So Q1 is 0.1202. 1202. So Q1 by A1, it gives us 0.1202 by 0.0314. That gives us actually 3.828 meter per second. And Q2 is again 0.02978 divided by 0.00785. That gives us 3.7936. 3.7936 meter per second. It is 0.02978. This actually we can put it in the next slide. So yeah, I'll give a quick recap because there were few number changes while we were doing. So first what we are doing, we are writing the two equations, that is Q is equal to Q1 plus Q2 and H1 is equal to H2, and H we know as FLV square by 2dg. So everything we know, we are substituting in the original form, and V is equal to Q by A, and that form we are using consistently throughout. So after substitution we are getting H as a function of F and Q. So now we need to determine friction factor F, and since we have F requires Reynolds number, we are calculating the Reynolds number. This is not needed. So Reynolds number is rho v d by mu. Again we are substituting everything known and rewriting it as an unknown equation in terms of unknown Q. So from this particular thing, what we are getting to know is Reynolds number is a very high value. So we are neglecting the Reynolds number dependence in the friction factor term, and we are neglecting that particular term and using the rest, and we are calculating F. Now after F calculation, what will we have? We can now previously H was a function of F and Q. Now we can write it as H as a function of Q alone. So H as a function of Q we are writing, and we know Q1 plus Q2 is equal to 0.15. So after that Q1 is equal to this is one equation, and the next is H1 is equal to H2. From that also we will get two equations, and equations in terms of Q1 and Q2. So we have two equations in which we have Q1 and Q2. So two equations, two unknowns we can easily solve. So we have, from equation 1 we are substituting Q1 in this particular equation, and we are getting a quadratic equation from which if we solve we will get Q1 and or Q2, whichever it is. Okay, we are substituting for Q1, so we will be having Q2. So Q2 we will write the equation and we will get it. After getting Q2 we can substitute Q1 and we will get Q1 equation as well. So for cross checking, what you can do is you can calculate H1 and H2, and if it is almost similar you are getting the right answer. So that is for question 12. Once again. Okay. So now what we are going to do is velocity in pipe 2. Again we need to calculate, I think Q2 by A2. Q2 is 0.02978 divided by A2, that we got as velocity as 3.7936 meters per second. So question 13 is also right. Now we have to calculate Reynolds number in pipe 1 and pipe 2 are respectively dash. So now we have to substitute everything. It was not 3.57, right? What was V1 value? V1 was actually 3.828, and this is this one. So Reynolds number is equal to rho v d by mu. So Reynolds number in pipe 1 is rho v1 d1 by mu. Reynolds number in pipe 2 is rho v2 d2 by mu. So 3.8, what was that? 3.828. So we can just substitute 3.828, and here we can write this particular value. 750 into 3.828 into 0.2 divided by 0.0002. It is 71000. And again, Reynolds number in pipe 2 is 750 into 3.7936 into 0.1 divided by 0.0002. Again it is oh come 426,600. No, something is off. Just give me a minute. 750. Okay, 47. Okay, 432871. Okay, same only. So actually we can cross check. Like we got this right. 23885350.32 into what was our Q1? It was 0.02 0.1202. That again gives us 2871, that relation. 71019. Yeah, almost similar, slight variation. But from there also we can get the Reynolds number values. So Reynolds number is rho v d by mu. So in pipe 1 it is rho v1 d1 by mu, and pipe 2 it is rho v2 d2 by mu. So v1 and v2 we found in the last problem itself, and d1 and d2 is already given in the question. So substituting that, we will be getting the solution. So that is for question 14. In question 14, what is asked? Friction factor in pipe 1 and pipe 2 are dash and dash respectively. So this is what I meant. Previously we neglected the Reynolds number accountants in the friction factor calculation while doing the problem, because we found it Reynolds number value to be very high. So we thought that it would be not affecting the value significantly. So now after we found out the Reynolds number values, we will just substitute it back in that and we will get the solution. So first we'll write the Reynolds number which we calculated. So we can copy it together. So this is the original equation, and this is not needed. We just need the values, right? So just we got a new value, so that's why I changed everything. Oh, sorry. Okay. So now we have to substitute this value in here, and we can substitute this Reynolds number 2, that is in pipe 2, for while calculating the friction factor in pipe 2. So this is this. So again this is 0.0075. 0.00075 divided, okay, can I come to that again? 2871000 to the power of 0.9, and what is in the 5.74 divided by this, plus 0.00075 divided by 3.7. That gives us this log. When we take, it is minus 3.67, and we have to take the square, so it becomes 13.50, and 0.25 divided by this 0.018. And F2 it becomes I'm just substituting and checking actually. 0.0015 divided by 3.7 and we are taking log and we are taking square and 0.25 divided by this 0.0219. It remains the same. So f1 and f2 are 0.0185 and 0.022. So previously in the while solution what we got a similar value only, similar number 0.018 and 0.022. So it didn't make much difference. So here also it is almost the same only. So friction factor in pipe 1 and pipe 2, if we go with the original formula where we are including the Reynolds number and still we are getting the same solution. So that is that means like our assumption is true over here. So that is what we can say. In question 16, what we got is the volumetric flow rate in pipe 1 and pipe 2 are dash respectively. So actually we calculated the volumetric flow rate in pipe 1 and pipe 2 values. We found it in the initial solution itself. So we can directly give the answer from that. So it is Q2 is 0.02978 and that one is 0.1202. Yeah, like 02978 and 0.1202. So we can give it a direct substitution. So it is Q1 is 0.1202 meter cube per second and Q1 is 0.1202 meter cube per second and Q2 is 0.02978 meter cube per second. So that is for question 16. What we got in 17 is pressure drop in pipe 1 and pipe 2 are dash kilopascal. Okay. Here we need to check actually. Q1 and Q2 values also changed. So I am just redoing the calculation simply because numbers got changed, which error we identified only now, right? So I am just changing that. So pressure drop delta P is equal to rho g HF. So HF we need to know. For HF we obtained the relation as a function of Q1 Q and H1 in pipe 1 it is 558.3 into Q1 square. So we know Q1, so it is we can directly substitute as H1 point 0.1202 square into 558.3, that is 8.06 meters, and similarly H2 is 9098.18 into 0.02978 square, that is again 8.06 meters. So H1 and H2 we calculated. This expression which we are using here, these two are what we obtained from the previous question. So we are doing direct substitution only. So apart from that, delta P is equal to rho g H. So rho is actually 750 into 9.81. The rho g into H is 8.06. It is actually 59301.45. 8.06. In other words, it is in kilopascal it is asked, so it is 59.3 kilopascal. So delta, actually, like, don't stick with numbers because these are kind of not making sense actually to say, but let it be. For our understanding of how to do the problem, this is sufficient, but number wise it is not even making sense. So delta P2 also we are taking, and we delta P1 and delta P2 pressure drop in pipe 1 and pipe 2 are same because it is connected in parallel. So that is the ultimate thing which we are seeing. So question 17. So with that we are actually kind of closing the problems related to that particular figure. So similar problem we have stretched enough and we have got the solutions for whatever the things that were asked in the question. So next we go to Another question, before that we'll see have figure. So we have three particular reservoir type from which are connected in junction. So L1, L2, L3. So and it is at height Z1, Z2, Z3. Consider the three reservoir system shown in the figure. All pipes are 15 centimeter in diameter and made of unfinished concrete. So yeah, we are given a three reservoir system and we are given the diameters of the pipes which are 15 centimeter and it is made of unfinished concrete. So we'll see what is asked. Question 8, in sum of all volumetric flow rate is dash meter cube per second. So it is actually 0 because it is connected in a junction and it is like, therefore it is kind of in a loop thing. So it is a 0. Similarly, the next question is sum of all flow velocities is dash meter per second. Again, this is 0 because it is connecting in a junction. So we are taking according to the concept the net flow it is therefore 0. So now coming to the last question in today's session, I think this is also a theory question only. If the velocity profile in flow is uniform, what is the value of the kinetic energy correction factor? So what is given? We are given that velocity profile in a flow is a uniform, that is in a plug flow. What will be the kinetic energy factor? So when does kinetic energy factor come into picture? First, when the flow is non-uniform only, kinetic energy factor comes into the picture. So when it is a uniform flow, what is the value of the kinetic energy correction factor? It is actually 1. So we are given few options. We'll first look at that. Option A 0, option B 0.5, option C 1, option D 2. So answer is actually option C because we are when the flow is uniform, there is kinetic energy factor actually becomes 1 because it is a ratio of the average actual to the average, right? Yeah. So if both are same, it is actually 1. So answer is option C. 1 is the right answer. So yeah, with that we conclude today's sessions. If you have any doubts, we can discuss. Or yeah, next week will be the last session. So if you have any doubts from previous sessions, also we can discuss in next week. So you can ask me next week if you have any doubts from previous sessions. All right. Yeah. Okay, I'll close today's sessions. We'll meet again next week, same time, 3 to 5. That will be our last session. So if you have any doubts, please do join the session and you can ask. We'll discuss more on that next week. Thank you for attending today's sessions. We'll meet again next week. Thank you.